And there we. Okay, with me. Okay, so that's what we have here, and that's the first piece. If you allow me to replace this, and there is a second piece there, that's mu naught, right? So that's minus mu naught over 4 pi. Again, 1 over r, and that's just I hat, right? So that's simply I vector I times c. Suppose again, you see this 1 minus r hat showing up, right? So this is equal to mu naught over 4 pi times minus of 1 minus r hat dotted with vector I times c. Okay, so write the c with mu naught. And you get the same feature that was coming in here, and use that cross product identity to show that this is mu naught c over 4 pi. Oh, there's a 1 over r. Right over r, 1 over r, and this is r hat crossed with r hat crossed with I hat or vector I. Use this piece in there, and you learn that vector E is CB, magnetic field, crossed with or hat. Okay. And that's your result in a sense. Let me put this all together. So if you have a radiation, first define this quantity, I times C, let's say, C times I, which is E cubed. This is your source. Who creates radiation? There has to be a change in the current density, or it could be time also. Sorry, charge also. Charge could be changing, or current could be changing. It's convenient to think of it as a current when you're thinking of antenna, but charge distribution also changes. The moment you have a current, you think about magnetic field. Magnetic field in the radiation zone is equal to mu naught C over 4 pi times vector I crossed with r hat over r. Okay, that's what we have. And electric field, once you have a magnetic field, electric field is straightforward. It's just a cross product of that, right? So it is equal to C times B. So you don't have to do any extra work. Okay. Let's visualize this a minute. Right, you have a current. Let's pick your current I hat at some point. This is your antenna, let's say. That's your vector I. Right? Don't notice this is this whole thing. This is a lot of things has to contribute to that. But imagine that whatever that is having this is imagine this to be your antenna if you want. You are standing somewhere here very far away. That's your r hat. That's your small vector unit, but that's your vector r, or let's say r vector r, let's say. So r hat is in this direction. Where is your magnetic field going to be? I hat crossed with r hat. So that's going in. That's your magnetic field. C times B. Or B, let's say. That's the direction of B. going into the board, right? It's tangent to the surface, it's on the surface, right? Not in the radial direction, it's perpendicular to the radial. What about the electric field? Cross the dotted with R, that's your electric field. What's the direction of propagation of this wave? It is going radially out. Right? These, you can show that this will always satisfy E dotted with B is equal to 0. And E crossed with B will be along R hat times this will be the energy density if you want. That will always, so that's the momentum if you want to. It is up to some units, right? Some constant. E times H, that's 1 over mu naught. So I think it is C squared, I'm not sure. Maybe mu naught, 6 squared. And remember, this is these are the properties of a plane wave. Right? If you have a plane wave, that's your electric field, right? That's your magnetic field. Magnetic field, is that clear? Right, that's your magnetic field E, B. They also satisfy the same equation. So these are radiation fields, they can be broken into monochromatic waves immediately. But that's your radiation is very simple. And there's no R dependence. It is usually the angle dependence that you're interested in. Like when you look at the sky, you don't care for where the stars are. It's always, is it in this direction? Is it in this direction? It's an angular dependence that matters.
What is the U of these?
U is energy density.
Is it included in that equation?
No. Yeah, it's in this. So U is, if you want, energy density epsilon E squared plus mu naught. And it's also true that in this case, electric field magnitude is equal to magnitude of the magnetic field. That's because of all this perpendicularity. Magnitude of the electric field will always be the same as magnitude of the magnetic field. Again, those are simple things you can derive or check out on those things. Because of the R hat, and this is perpendicular to each other. Okay. That's all. And you will, in your homework, hopefully be able to explore this for a simple antenna. Double simple antenna. Once, if you have just one wire, it is a simple antenna. A wire of length L is a simple antenna. If you put two of them, it's reasonably compound. But research in antenna is very advanced. This is the simplest thing we will do. But antenna is by trial and error, they have made a lot of progress. Significant amount of work once done. Okay, that's all. Thank you. And I need to run because I need to complete. Oh, it requires this computer. Yes, sir.